Okay, so let's start. Being a holiday, see the amount of number of students who are joining. It's so sad, right? Okay, so let me see before I start. How many of you have read the book at least once? Just raise your hand. Yeah, one person. Okay. Ah, okay. Right. It's only very few out of the body. Right. Thank you. Right. Now, how many of you are repeating this course? Just raise your hand. No, all newly registered students. Very good. So, those who have read the book, what did you understand? Did you understand what was given in the book? Just give me your idea. I need to hear your voices, right? And I would like to
Some
know
part,
your views. Yes,
some parts are not clear, madam.
parts are not clear, but you could understand.
Symmetry, it's okay, but inversion and the
So, okay,
last part,
I will try to explain with the structures, right? So we will see at the end. Right, okay. Now let me share the screen. Now I have taken some structures, most of the structures from the web, right? Okay. So can you all see this screen?
Yes, ma'am. Yes, ma'am.
Talk loudly. I'm an old woman. I can't hear properly. Right? Right, okay. Please concentrate on this because for me, I also went through the book this only first time. And then I prepared my own presentation by taking certain things from the web. Right. So we are going to discuss symmetry in molecules. That is your unit 4 under CYU 4300. Right. So now here you see a picture. What is it?
Butterfly.
It's a butterfly. So when you see, look at a butterfly, do you get any feeling that there is some sort of something? Right? Yes or no?
Yeah. Yes,
Yeah.
madam.
You can see something in there. Right? Similarly, now here, symmetry in nature, we get the leaves, right? This is the maple leaf and magnolia. All these things, by looking at that, you can see there is something. And we call it symmetry. Those are symmetrical objects, right? The butterfly is symmetrical. The maple leaf is a symmetrical one, right? So you have seen several things. Now here you can see a flower. Now in the earlier case, what we can see is it is only one half is equivalent to the other half, isn't it? Only one half is equivalent to the other half when you take this butterfly or the leaves. But when you take a flower, right? Now here, there are several places you can divide it into two, isn't it? So along the different petals, by bisecting, you can see you get symmetrical flower. So these are symmetry in nature, right? We call this a symmetrical object. Now let us see symmetry in molecules. Now when you look at this ammonia molecule, okay, right, when you see this ammonia molecule, do you see anything there? some sort of symmetry, or the ethylene molecule, or the dichloromether. So we are going to study the symmetry in molecules. Okay. So here you can see the water molecule. So the red color circle is oxygen atom. The two blue color circles are hydrogen atoms, right? So this is the three-dimensional picture. And you know water, the geometry of water is what?
Try.
Sorry? Water, the geometry. You must remember those things because when you study the symmetry, you have to visualize the three-dimensional structures. Then it's easy. So this is a bent molecule, right? And what is the angle of the water molecule? The angle of the water molecule?
120.
Hmm? What is the hybrids?
125.5.
Very good, very good. Okay, right. So here now you see this oxygen in the middle and two hydrogen at the two bonds, right? They are lying in the 105 angle. But when you look at this picture, it lies on the plane of the paper. Now in this case, we have the plane of the screen, right? So this lies in the plane of the screen. Okay, the three atoms lie in there. And you can rotate this. When you rotate it, what happens? You rotate it 180 degrees, right? It turns the other way around, and this hydrogen atom label 3, which is on my right side, will come to my left side. And the hydrogen atom is labeled as 2 will come on to the right side. Now you see how this is done, the rotation. You have to visualize. Okay? So it is rotated through this oxygen atom, right? You only turn it the other side, 180 degrees, along this plane of the paper, right? You turn it, and again it lies on the plane of the paper, but the two hydrogen atoms have exchanged their positions, right? So we will go further. So these things, we call them configurations, right? Now, structure of water, when you draw it two-dimensionally, earlier we saw the three-dimensional structure. This is the two-dimensional structure, right? Now, this structure, we can see there is a green hydrogen atom and a red hydrogen atom to make it easy for you to understand, right? And this is labeled as A. So, when you rotate this by 180, the two H's are on other sides. Okay? The one which is red color, we will consider red color hydrogen atom, which is very visible. So that is which is on the right side of me, turns to the left side. And when you rotate it again, what happens? It comes to the original position. So here we have done some work, and we call this rotation an operation. So in symmetry, we talk about operations and symmetry elements. So let us see how we could explain this. Now my next figure gives you this equivalent and identical configurations. Now the same thing. The A molecule, after rotating 180, you get the B molecule, right? And if you rotate again 180 degrees, you get the C. So here you see A and B looks the same, right? Only thing is the orientation of the nucleus, hydrogen and the two hydrogen atoms have changed. So therefore we call this an equivalent orientation. It's a equivalent orientation or equivalent configuration. And when you rotate it by another 180 degrees, you get the C molecule, or you get this configuration. So here we see the hydrogen originally in red color is here again in red color. The other hydrogen also in the same place. So each nucleus comes back to its original position, and that is called an identical configuration. Right? Now, did you understand this?
Yes,
Yes
madam.
or no?
Yes, ma'am.
Yes, madam.
So you should be able to distinguish equivalent and identical configurations. Right. So this is the source I got. So usually an identical configuration is an object having the original position after doing an operation. So in the earlier case, so identical orientation is the when you do an operation, you get the original position. So that is called the identical orientation. Then equivalent configuration or orientation, it's an orientation indistinguishable from the original position. It looks the same, but indistinguishable, right? So that is called an equivalent configuration. Right. So indistinguishable nuclear configurations of a molecule are said to be equivalent. We saw no indistinguishable orientations are said to be equivalent orientations. Equivalent nuclear configurations of a molecule are not necessarily identical, right? So remember that point. Now we'll come to symmetry operation or the action that we do. Okay. Now it is a movement of a molecule. Symmetry operation is a movement of a molecule. Now after the movement of the molecule, every nucleus coincides with an equivalent nucleus of the molecule in its original orientation. Right? So first you do a movement, that is the operation. So after the movement, the molecule, every nucleus coincides with the equivalent or the same nucleus of the molecule in its original orientation. So that is a symmetry operation. You have to find the same thing, same nucleus after the operation also in similar positions. So that is called a symmetry operation. So then symmetry element is in general is a geometric element. It can be a line or a plane or a point with respect to which one or more symmetry operations of a molecule may be carried out. So it is either a line or a plane or a point with respect to which you do symmetry operations, either one or more of a molecule. So those are symmetry elements. Right, we will see symmetry operations and symmetry elements. Now, symmetry operations, there are several operations. We have to learn rotation. We have already seen that. Then reflection, inversion, and improper rotation. Now, this first one is usually in certain books, it's called as proper rotation also, right? Right. So, the symmetry elements which gives you with this kind of operation is also termed in different ways. If you do a symmetry operation rotation, you get axis of rotation, that is the symmetry element. For reflection, symmetry planes, and inversion, inversion centers, and here for improper rotation, you get improper axis. So these are the actions we do for the movement: rotation, reflection, inversion, and improper rotation. So you have to learn only 4 of these, right? This whole book is based on that. Then the symmetry element corresponding to each of these operations are axis of rotation, symmetry planes, inversion centers, and improper axes. Right. So the symmetry operation which takes a molecule to an identical configuration is called identity operation. So in addition to these four operations, there is another which all molecules will possess. The symmetry operation which gives you a molecule to an identical configuration, and that is called identity operation. So therefore, we have 5 types of symmetry elements: identity, rotation axis of symmetry. So these are the different terms that are used, right? Axis of rotation. In your book, it is axis of rotation. Rotation axis of symmetry also the same thing. Plane of symmetry or symmetry planes, right? Then center of symmetry or inversion center. And alternating axis of symmetry or improper axis. So these 5 things only you have to study. So here there are 4 actions: rotation, reflection, inversion, and what is the other one?
Improper.
Yes. Improper rotation. This is rotation axis, proper rotation. Here, improper rotation, right? So the 5 actions are there, right? So let's take one by one and see. Before that, now for identity, the symbol that we give is E, and we do nothing. It's the identity of the molecule. The plane of symmetry or symmetry planes, it is sigma, denoted by sigma, and the operation is reflection, rotation axis, Cn. This superscript M is also there when you do it, say 1 or 2 or 3 times like that, it gives you that, right? So Cn is the symbol, M is the number of times the rotation is carried. So this N is called the order of rotation. We will learn those things. Improper rotation, Sn. So for improper rotation, we use S. N is the order and M is the number of times you do the action. Okay. Then inversion center, I. So symbols are E. Identity, sigma. Symmetry planes, Cn rotation axis, improper rotation Sn, and inversion center. Right. So we will see rotation and axis of rotation. Now Cn is the symbol for that. We already saw water molecule. We called about this n-fold rotation. Cn means n-fold rotation. So n-fold rotation is a rotation of 360 upon n about the Cn axis. So there should be an axis where you rotate. Now in this earlier case, water molecule, you see along this axis only we have rotated, right? You rotate it along this axis. So it's a n-fold rotation axis. Now here we have rotated it by 180. So what is the value of n? What
Two.
is the value of n?
2.
2.
Two.
Very good. So you have to divide 360 by this angle, then you get the order. Or if you know the order, you divide it by that, then you get the angle. Okay? Right. So here, do you see this axis? It passes through the oxygen atom. And you rotate it 180 degrees. Right. So again, the axis of rotation, order of rotation, you can have 2, 3, 4, 5, 6. Okay. Depending on that, the angle changes. If it is 2, 180. When it is 3, it is 120. 4, it is 90. 6, it is 60. Now, when n equals 5, what is the angle? When n equals 5, What is the angle?
72.
72. Very good. So here I have listed few examples. We will go through one by one. Okay? Right. Now here you see this again.
45.
Sorry. Did anyone want to say anything? Right. Here you see again the water molecule. This also I got it from the web. Okay. So this is, we said the axis is this rotation axis. It goes through the oxygen atom. So the rotation is done like this, right? And you get an indistinguishable molecule. So here we have this 180 degrees. It is a C2 rotation. So two-fold rotation, you get n equals 2. Right. So C2 rotation, we will further explain. Now this is again the same thing, water molecule. We have labeled this as H1 and H2 in this, right? And this molecule is labeled as A. You rotate it through this 180 degrees, you get the two positions exchange, right? Because the molecule, we have done a C2 operation, C2 rotation. You rotate it by 180 degrees and then you get the C2B molecule, right? So, one more. Okay, sorry. Right. So here we rotate it by 180 along this axis. And then you get molecule B. You rotate again by 180. You get the molecule C. So A and B are equivalent configurations. A and C are identical configurations. Right? So here we have done the C2 operation how many times? Twice. This is the first C2 operation and this is the second C2 operation. So after doing two C2 operations, you get identical configuration. So identical configuration, we give the symbol identity of the molecule E. So when you do two operations of C2, you get an identical molecule, right? So it equals to identity symmetry element. Then we'll take C3 rotation, right? Now look at this BF3 molecule. Here this F is in different color. So you do 101 thing. BF3, what is the geometry?
Square plane.
Sorry?
Trigonal
Plane.
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 Trigonal plane. Yeah.
Right
So it
plane.
lies in the plane of this screen. Okay? So you rotate it 120. The F atom, which is in different color, will change the position. And you do another 120 operation. Again, it changes the position. Right? To bring it to the original, you have to do another 120 operation. Now, so rotation of this BF3 molecule in 180 degrees angle, you get the equivalent configurations. And the third one, when you do, it will give you the identical operation. Okay. So 333 means it is equal to what?
Original configuration.
Original. You call it what?
Identity.
Identity. Very good. Right? Okay. So here the same thing, but little bit different because here this is a planar molecule. Now when you look at ammonia, right? What is the geometry there?
Pyramid.
Pyramidal, right. Now here one hydrogen lies in the plane of the paper, one goes out down, and then one comes out up the plane of the paper. Okay? So again, you can view this from the top also. I'll show you that later. So you rotate this by 120, the hydrogen atom positions changes like this. So 120 anti-clockwise, H1 goes here and H2 comes here, right? And H3 comes above the plane. So again, when you rotate it 120, you get the C molecule, which is equivalent. And then when you do another 120 operation, you get the D. So here again, the axis passes through the nitrogen atom. We have the rotation axis, which passes through the nitrogen atom. And we rotate it via that. Okay? So here this is another example of a C3 axis. So when you do 3 times, what happens? You get the identity operation. Okay? So C3 thrice means you get identical molecule. So A and B and C are all equivalent configurations. A and D are identical configurations, right? So when you do C3 3 times, you get the identical molecule. So C2 2 also, you get the identical molecule. So do you see any relationship there? Hmm? Yes or
Order
no?
and number of.
Yes. Yeah, okay. Here now, if you look at the ammonia molecule from the top of the nitrogen atom, right? If you look from here, this is what you can see. Now, it's not a planar molecule, right? But you can see, view these hydrogen atoms like this. And when you rotate again, it changes the positions, right? Okay, so C3 axis of rotation in ammonia molecule. So Cn to the power m, or m is the superscript, n is the subscript, Cn we know is the rotation axis, symbol for rotation axis. So superscript m represents the number of times the rotation is carried out, right? So earlier we saw C2 2 and C3 3, right? So if you rotate it once, you can say Cn C2 1. If it is a C2 rotation axis, if you do it once, C2 1 we never put M1, but if it is C2 2, we have to show it, right? So and the M superscript gives the number of times you do the rotation. Similarly, there is another Cn is equal to E. So we saw C2 2 is an identity operation, right? If it is C3, it is 3 times. You get the identity. So that indicates the rotation is equivalent to an identity operation. So if it is C4, which operation will be equal to identity operation? When you have a C4 axis.
4.
C4, 4. It's very simple. So Cn to the power n, right? N is the number of times. Hello? Any question?
Madam, can you explain how to
Which
get
one?
order?
Order.
Yeah, it's not clear.
Order is this now. You get the order. If you know the angle, you divide 360 by the angle, then you get the order,
Okay, ma'am.
right? So
Okay,
here
thank
we
you.
rotate it by 120. So it's a C3 axis. You got it? For water
Yeah, ma'am.
molecule,
It
we had
means
C2
means
because
C2 means it rotates by 180.
180. Yes.
Thank
If
you,
it
ma'am.
is C4, then what is the instance for?
19 degrees.
90 degrees. Right?
Oh, yeah. Thank you, ma'am.
So it's very simple. Right. So C4 four times, you get the identity. Everything is like that. Right? Okay. Now I'm not doing the whole book, right? I will cover the major areas which you find it difficult, but you have to go through the book again, right? Then you will understand it better. I'm only helping you to understand the content in the book, right? Because within these 2 hours, you cannot cover the whole book. Important areas only I will be explaining, right? So here you see a trigonal planar molecule. Example what? Trigonal planar BF3, yeah, boron trifluoride. Okay. So here in BF3, this is a planar molecule. No? So this is the three-dimensional structure. So we know it has a C3 axis because rotation by 120, you get equivalent configurations when you rotate by 120. Okay. In addition to the C3 axis, there are C2 axes. Okay. So how do you get that? So if you take the boron and the fluorine atom along that axis, if you take one axis, it can be rotated through 180 to get an equivalent orientation. So you have C2 axes in addition to C3 axis. So along the BF bond, there are 3 C2 axes in this molecule. Is it clear?
No.
Now this is C3, okay, which passes through the boron atom. But if you consider the boron and fluorine bond, and if you draw a line to show the axis, that is a C2 axis, because when you rotate it 180, you get the equivalent configuration along this axis, right? So there are 3 C2 axes. I'll show you another with the two-dimensional figure, right? So before that, now we said here there are 2 kinds, C3 axis and C2 axis. So any molecule, depending on the structure, can have more than one rotation axis. Okay. So here we have 2, C3 and C2. 2 types are there. So the rotation axis, which has the highest order, is called the principal axis. Okay. So the rotation axis, which has the highest order. So here in this BF3 molecule, C3 is the highest order. So therefore, C3 is called the principal axis. Now you see, right, here the BF3 molecule, the planar molecule is drawn like this, right, the two-dimensional structure. So along this BF1 bond, we have a C2 axis. When you rotate it, you get the equivalent configuration. So by drawing the axis which contains the BF bond, there are 3 BF bonds. So there will be 3 C2 axes in this BF3 molecule in addition to the C3 axis. Okay? Right. So the same thing we have drawn it in the planar molecule. Okay? So within this we have the C3 axis. Okay, along the boron, it passes through the boron atom. But whereas the C2 axes are along the BF bonds. So one C3 axis and there are 3 C2 axes in BF3 molecule. Okay. So C3 is the principal axis. Is it clear?
Madam, through C3, we can only rotate, no, by 120. And
So
C2,
these are rotation axis. I'm referring to because CN means rotation axis. The symbol CN stands for rotation axis.
rotation.
Right?
But C2, madam, we can, is it, that is rotate by 120, 180.
180.
Okay.
So along this bond only you have to rotate. Right? When you rotate it once, right, along the BF1 bond, we will say F2 will come onto this side and F3 will be on the other side. Since we have labeled only, we say like that, but you get the equivalent configuration.
C3 is going through only B, no, madam?
It's
Through
going
only
only through B.
B.
That is why I showed you the earlier figure.
Okay. Okay,
This
madam.
one.
Yeah.
This is clear. So this is the plane of the molecule, right? And C3 passes like this. If you want to understand this better, try to make some models and see, right? Then you will understand. So the axis which has the highest order is called the principal axis, right? So along these BF bonds, you get C2 axis. So since there are 3 BF bonds, you get 3 C2 axis in this BF3 molecule.
Madam, excuse me.
Excuse
And
me,
so
madam.
Yes.
Madam, when we consider the C3 axis, aren't we consider the symmetry of this molecule?
I didn't get it. C3, yes, C3 is there.
Yeah. Is it not a symmetry, no? So
It's a
aren't we
symmetrical element, no? Rotation axis is a symmetry element, right? So you do the operation 120, you get the equivalent configuration. You do it again, you get another equivalent configuration, right? Similarly, C2 also, you do the, we rotate it by 180. Then you get the equivalent configuration, right? You rotate it through BF3 bond in this molecule, right? So you rotate it 180, you get the equivalent configuration. For you to understand only, I have labeled as 1, 2, 3. You see that?
Yeah, it's okay.
If we don't, we cannot distinguish if the 3 fluorines. For you to understand, for me to explain only, this is labeled as 1, 2, 3. Right?
Okay.
Another person wanted some clarification.
Madam, and also C3 are perpendicular to the plane and the C2 are parallel. Is it?
No. C3 goes through this boron atom, no?
Atom
It is
and
perpendicular to the plane of the molecule.
yeah.
Plane
And
of the molecule. Others
C2
lie in the plane of the molecule.
okay.
Right? C2 axes are in the plane of the molecule. Okay? Right. So we'll go to methane, CH4 molecule. Right? Now, do you think you have rotation axis here? Yes or no? Not sure. Right. Now, C3 here, CH4 again, along the CH bond, right? You consider this as the ammonia molecule. Here, 3 hydrogens, two actually lie on the plane of the paper, the other going through the plane, going inside, and then other one coming outside, right? So here, if you take this as one rotation axis, you can see 3 hydrogen atoms. You can move it 120 and you get a C3 axis along this CH1 bond, right? Similarly, for all these things, you can have C3 axis along this carbon-hydrogen bonds in methane. similar to ammonia, except the difference is the axis lies along this CH bond, right? This is a tetrahedral molecule, but if you look at this part only, it is similar to the ammonia partner, right? So we had a C3 axis in ammonia. At C3 axis lies in this CH bond. So if you take this, it's the same. If you take this, because we drew it like that, right? I'll show you another drawing here. So each one has C3 axis along the carbon hydrogen bonds. And you rotate it by, what is the angle?
120.
120. Very good. Right. So in addition to that, the methane molecule, again, you can find C2. C2, because now here these two lie in the plane of the paper. One is coming out, the other one is going in. So you can have a C2 axis along this carbon atom and you get equivalent configurations, right? So you can rotate 180 degrees and get the equivalent configuration. So here we have, initially we said it has C4. In addition to that, it has C2. So which is the principal axis here?
C3 axis.
C3, sorry, not C4, it's C3. C3 is the principal axis, right? So this is another example. Then, okay. Identify the symmetry elements in an ethylene molecule. Now I have given you the structure and indicate the principal axis in this molecule. This is again another planar molecule. Where do you get the symmetry elements in ethylene molecule?
C2 axis.
Yes, where?
Along the
Where do you get it?
Along the
Along the
CC
double
bond.
bonds.
Along this bond.
And also
Carbon-carbon
the
bond.
perpendicular to the
Very
double
good.
bond.
So here, there is a C2 axis along this, right? You can rotate it 180. Similarly, you can, the midpoint, right? You can have a C2 axis. You rotate it by 180, you get the equivalent configuration, right? So, and here, this carbon, this axis, C2 axis is called the principal axis. Why? Because it goes through the maximum number of atoms. So principal axis is either the highest order or one which goes through the highest number of atoms. So in this case, we have two C2 axes. One which passes these two carbon atoms is called the principal axis. Right? Clear? Any doubts? No. Everybody understood? Okay, good. Right. We'll take the square planar complex, right?
Madam,
XCF4.
excuse me,
Yeah.
madam, the previous example, how many C2 axis?
2.
2.
One along the CC bond and the other one, you take the midpoint, right? Through that. Now, this is clear in that case, right? So it's a planar molecule. It goes through the C2 axis in the center of the molecule, right?
Okay, madam.
Okay. So we'll take square planar complex. Now by looking at this, do you see any rotation axis here?
C4.
C4. What is the angle you rotate?
90 degrees.
90 degrees. Very good. So here, there are C2 axes, right? C4 is also there. C4 is the principal axis. But along the F xenon F bond, you can get C2 axis. You can rotate it through that. Or, so there are two C2 axes here, right? Then, in addition to that, you can have C2 axis like this also, which bisects the FXEF bond. So you get another C2 axis here and another C2 axis here, right? So how many C2 axes are there? 1, 2, 3, 4 in this square planar compound. In addition to that, you have the C4 rotation axis. C4, 90 degrees, you get this. So we have C2 axis here and C4 axis in this, which passes through this. Again, through the xenon, this rotation axis, C4 also is a C2 axis. So when you rotate this consider molecule A, you rotate it by 190, you see the change of positions of these labeled atoms, right? And when you do it again, you get this configuration, right? So when you do twice C4, you get a C2 operation. See, 90, 90, 180. You rotate it by 180, you get this orientation or this configuration. So when you do C4 operation twice, you get a C2 operation. That is equal to C2. Okay. So here in xenon, like F4 molecule, you can have C2 axis along this, which passes through this xenon atom, right? In addition to C4. C4 is the principal axis. Okay. Any doubts? I will try to explain as much as possible using examples, then it will be clear to you. Right. So we'll take ethane molecule, the staggered form. Okay. So this is the staggered form. These two H's lie on the plane of the paper. These two are going up, down, and these two are coming out of the plane. Right? So you can see there is a C3 axis along this carbon-carbon bond. Okay? So we can represent it like this. Because here, if you take the rear side or the closest carbon atom, the 3 hydrogens are like this. And in the other carbon atom, the hydrogens are like this. So here, in this molecule, staggered ethane, there are C2 axes which goes through, which bisects the 2 hydrogen atoms in each case. When you write it like this only, the Newman projection only, you can give the C2 axis. In addition to that, you have the C3 axis which passing through this CC bond. That is what is shown here. Okay? Is it clear? Staggered form of ethane. You have to visualize this, right? 3 hydrogen atoms. Here, these hydrogen atoms, which goes through the other way around, right? And in Newman projection, you should know how to draw that. So here, the center is a C3 axis, which goes through the carbon-carbon bond. In addition to that, right, we have C2 axis, which bisects the hydrogen-hydrogen angle on the two carbons. Yes or no? Is it clear?
It's clear, madam. Can you
This
show the
C2
previous?
axis? Sorry,
Can you show the previous slide, madam?
previous slide. This one.
Uh, yes, madam. Can you explain this rotation, madam? Because when we rotate this,
This is
yes,
C4
it,
molecule, right?
uh,
So here you rotate it by 90 degrees, right? You rotate it anti-clockwise, and then here this F labeled number 1 will move here. F labeled as 2 will come here. F labeled as 3 here, and then 4 here, right? So it's the same. It has a C4 axis. You rotate it by 90 degrees. When you rotate it again by 90 degrees, again it changes the position. 1, 2, 3, 4. Right? Now the
yeah.
same thing, if you take these two A and C molecules only, this is a C2 operation along the same axis. Right? You rotate it by 180. This 2, fluorine labeled as 2 will come here. Labeled 4 goes there, like that. So it's a C2 operation also, in addition to C4. So when you do C4 2 times, you get a C2 operation. That means you do C4 2 times means 180 rotation. So 180 rotation, you get C2.
It's okay, ma'am. Thank you.
Hmm?
Clear, ma'am?
Clear? Ah.
Yes, ma'am.
So this staggered form of the ethane molecule. Is it clear?
Yes, ma'am.
Ah. So here you have the C3 because when you rotate, again, if it is labeled, you can identify easily. This hydrogen, when you rotate 120, it goes here. And this goes here, this goes here. So you get the identical equivalent configurations with 120 rotation, C3. At the same time, there are C2 axis, which bisects this hydrogen and hydrogen, these two hydrogens. These two hydrogens and these two hydrogens. So there are 3 C2 axes in addition to the C3 axis. And C3 axis is the principal rotation axis in staggered form. So when you go to the eclipse form, right? Again, you have the C3 axis, right? And now these hydrogens are overlapping on top of the other, right? So here we have this Newman projection. So along these carbon-hydrogen bonds, there are C2 axes. Whereas in the staggered form, it goes through the C2, it bisects the closest hydrogens, right? But in this case, eclipse form, the Newman projection, each hydrogen is overlapping the other hydrogen. So therefore, you can have a C3 axis and C2 axis along this carbon-hydrogen bonds. So there are 3 C2 axes, but the position of the C2 axis is different from the staggered form. Right? Okay. So we'll take benzene molecule. Again, it's a planar molecule. By looking at this, can you say what type of rotation axes are there in benzene?
C2 and C6.
C6 is what is the angle?
C6.
45.
45
45?
degrees.
60.
60. 360 divided by 6 is 60. So, yes. So, where does it lie?
Center.
Center. And C2 axis where?
Along the height.
Carbon hydrogen bonds. This bond, it's not the bond, it's passing through these two opposite hydrogens, right? So along that we have one C2 axis. Similarly, there are three C2 axes in the benzene molecule, right? So in addition to that, the H, this bond angle or this bond is bisected by another C2 axis. So there are another set of C2 axes, right? And in addition, we have the C6 in the center of the molecule. So altogether, there are 6 C2 operations, C2 rotation axis, and one C6 rotation axis. So C6 is the principal rotation axis. Now this C2 axis, we label, that will come later. C6, C3, and C2. In addition to C6, we have the C3 axis also, rotation by 120. You get the equivalent configurations. And also C2 axis, right? So in benzene molecule, we have these three rotation axes, C6, C3, and C2. Right. So this is examples I have taken for rotation axis.
121.
120, you rotate it and see. Now here, 60 means this HL will move here. No? But if you rotate it 120, it will move here. Again, equivalent configurations you get. Right?
Okay.
Okay. So that's all for a rotation axis. You try to make models and then rotate it and see. Right? You will understand better the axis that you have to rotate. Right. Then we'll go to reflection operation. Right? So two parts of an object after reflection through the plane produce an indistinguishable orientation. Two parts of an object. Now, after reflection through the plane gives you an indistinguishable orientation. Now, we saw at the beginning symmetry in nature, where the butterfly or the leaves, the flowers, they have you get two parts, which gives you indistinguishable orientations, right? So here we have under reflection operation, the symmetry planes or plane of symmetry, which is, the symbol is sigma, right? So if a reflection operation through a plane is a symmetry operation, then that plane is a symmetry element termed as symmetry plane. So you have to have the reflection operation, right, through a plane. And that plane is called the symmetry plane. Now, the earlier case, rotation axis, we did the rotation. Now we do the reflection. Okay. Again, we can explain it like this. A plane which passes through a molecule is a symmetry plane if a reflection of the molecule through it is a symmetry operation. So in the case of butterfly, if you keep a plane at the middle of the butterfly, you get two equal parts. So that's a reflection operation of a symmetry plane. Just give me 1 second. Okay. So that's called the symmetry plane and the symbol is sigma. So molecule can have more than one symmetry plane. Like the earlier case, rotation, there can be several rotation axes. So symmetry planes also, it may have more than one symmetry plane. And for a reflection operation to be a symmetry operation, mirror plane has to be kept in the correct orientation or the symmetry plane. We call it a mirror plane. It's easy to visualize mirror. Okay. So it has to be kept in the correct orientation. So there are three types of symmetry or mirror planes: horizontal mirror plane, vertical mirror plane, and dihedral mirror plane. So the horizontal mirror plane denoted by sigma h, and vertical mirror plane sigma v, and dihedral mirror plane sigma d. So here this horizontal mirror plane is perpendicular to the principal axis. So there should be a principal axis. We know what a principal axis is. It is perpendicular to the principal axis. And here vertical mirror plane contains the principal axis. It goes along the principal axis. And also it passes through maximum number of atoms. Dihedral mirror plane again contains the principal axis. So it's a vertical mirror plane and which pass through less number of atoms. And also it bisects angle between two C2X, right? So it bisects bond angle. We saw in the benzene molecule, there are C2Xs, several C2Xs, right? So in certain cases, they bisect, we see. So how many reflection operations can be performed about a given symmetry plane? Now here, consider this BF3 molecule. You know it's a planar molecule. You first perform a reflection operation along one of the BF bonds. So you take that BF1 bond and you keep a mirror. You get the reflection. F2 will come here and F3 will go there in the first reflection. Then you take that reflected molecule and then you reflect again, right? When you reflect again, what happens? You get the original molecule. Okay. So first operation gives you sigma, second operation gives sigma 2, right? And sigma 2 it gives you the identical molecule and it's an identity operation. So in a given molecule, only two operations can be performed about a given symmetry plane. So you get sigma 2 equals to identity in a given symmetry plane. Is it clear? Yes or no? People are listening to the election results. Where? Where are you all? Did you understand? I know.
Can understand.
Can understand. Only one person. Others?
Clear, ma'am.
Otherwise, I think that either you all are sleeping or you are listening to the election results. Right. Okay. So we'll move symmetry planes. Now we take the water molecule, H2O, right? Now we know this has a C2 axis, which goes through the oxygen atom. And though we write it like this, it's a bent molecule and it lies in this plane. So this C2 axis contains the mirror plane, right? And also there is another mirror plane. You can keep a mirror plane like this, which bisects through the oxygen atom and you get two equal halves. right? So here you get another C2 axis and also a mirror plane. So here we have the symmetry planes in water molecule. So is this horizontal or vertical mirrors?
Vertical.
These vertical mirrors. Good. Now we'll check the mirror planes in ammonia. Okay. So we know there is a C3 axis. And now when you look at from the top, this is the center of the molecule. And again you get a mirror. You can keep a mirror plane along this NH bond. So you get sigma V. So how many mirror planes are there in this ammonia molecule?
3.
3.
3. Very good. So you get 3 mirror planes along this NH bond, right? In addition, we have the C3 axis, right? So we have 3 sigma V's and which lies along the C3 axis, right? Symmetry planes in square planar molecules.
Excuse me, madam. Only 3 mirror planes, no? That.
Yeah,
See,
along this
3
NH bond, only along this NH bond only you get 2 halves, no?
Okay.
When you keep a mirror, you get the reflection of that. That is what it means, right? So here, similarly, along each NH bond, you can have 3 vertical mirrors. Okay? Clear?
Yes, madam.
Okay. Right. We'll take this square planar molecules. Right? So in XCF4, where do you get the mirrors? Sorry, the planes, symmetry planes. Just tell me one plane.
Along the
Along the
SCF
FCFC
bond.
bond.
Very good. Along the XCF bond, we have C2 axis. So in addition, we have, sorry, so along this we have C2 axis and also we have mirror planes along this C2 axis, right? So in addition, we have 2 C2 axis which bisects the FXEF bond, right? So these 2 bonds are bisected. We have 2 C2 axis there. So that also will contain the mirror planes. You keep a mirror, you will get the reflection. U equal halves, right? So in addition to that, the plane, it's a planar molecule. So plane of the molecule is also a mirror plane. And it is labeled as sigma H, horizontal mirror. Okay? So how many are there?
5.
Now, we have this C4 rotation axis, that is the principal axis. So all these lie along the principal axis, right? Except this, which is the plane of the molecule and perpendicular to the C4 axis. So it's a sigma H, right? So these mirror planes, now these mirror planes are called vertical mirrors. One which bisects 2 vertical mirrors is called the dihedral mirror plane, the dihedral symmetry plane. Okay, so it is also a vertical mirror, as I said in the beginning. So it bisects 2 sigma V's, right? So therefore, this is termed as sigma D. So here we have 2 sigma V's, 2 sigma D's, and sigma H in this square planar complex. right? So any square planar, not only this, any square planar complex, you will get this set of symmetry planes. Right. Then we'll move to this alene molecule. This is the structure of alene molecule. Do you see any symmetry there? Symmetry plane? Now here, these two. This carbon lies in the plane of the paper. Okay, so these two hydrogens are in the plane of the paper. Whereas this carbon is perpendicular to the plane of the paper. So that is why these two hydrogens, one is going inside and one is coming out. That way it is drawn, right? So these two are like crossing each other. Okay. So here you can see there are two C2 axes which crosses the, which gives, which bisects the two hydrogens. So this is not in this plane, these two hydrogens. So this can bisect these two. Similarly, the other. So here we have, this is called sigma D because two C2 axis. You can put a mirror, keep a mirror plane and then get sigma D. Right? This is also a sigma D. Right. So that is the alene molecule. Then the 2,2-dichloroalene. Now this is the plane of the paper. This is coming out and going inside the plane of the paper. So here this gives C2 axis, right? Along this there is a C2 axis. And it contains the mirror plane also. So there is one sigma V and another sigma V which bisects this chlorine-chlorine bond. So when you keep a mirror plane here, you get one hydrogen going inside, other one coming out. So these two will be having equal positions. And here it bisects the two carbon Cl bonds. So there are two sigma V's in this molecule. It's not a planar molecule. Only one part is planar, other part is not planar. It is perpendicular to this plane. So therefore, there are two sigma V's. Then again, the staggered ethane molecule. Now what do we have here? Rotation axis, C3 or C2. In staggered ethane,
C2.
C3. C3 and C2 also, right? So here we have C2, right? So there are three C2 axes. In between that, along this H carbon H bond, you get a mirror plane. And it is called the sigma D because it bisects two C2 axes, right? So we have two sigma Ds in staggered form of ethane, right? So this is with respect to inversion mirror planes, okay? So now you understood part of it at least. How many mirror planes are there or symmetry planes? How many symmetry planes or mirror planes are there? Come on. You have learned all this time now? Horizontal mirror planes, vertical mirror planes, and dihedral mirror planes. So only 3 times are there, right? Why? The silence does not give me an answer. Whether you understood or not, please tell. we talk about sigma Ds, sigma Vs, and sigma Hs. So sigma H is the horizontal mirror plane, sigma D is the dihedral mirror plane, and sigma V is the vertical mirror plane. Okay? So we'll move on. Inversion center, or you call it center of symmetry. So a point at the center of a molecule such that a straight line drawn through meets the same element at the same distance on either side. Inversion center is that. You take a point, the center of the molecule, and you draw a straight line which gives an element in one side, and you extend the same line on the opposite side, you meet the same element. So reflection of every atom group of a molecule through the inversion center leads to an indistinguishable orientation. We see, right? So here, inversion center. Now here you label this as 1, 2, 3, 4 and come to carbons A and B, right? Now if you take the midpoint of the molecule, this is the midpoint, right? And if you draw a line from H1 to this midpoint, and if you extend that line, you will meet another hydrogen molecule the same distance, right? So you can draw this. You take this midpoint and draw a line to this hydrogen, and you take this midpoint and extend that line. You find a similar atom. So this is an inversion center. Similarly, the other way around also, you can draw a line and then these two means similar atoms and equal distance. And along this also, through carbon-carbon also, you can draw the line and then you get. So this is called the inversion center in this molecule. So ethylene molecule has an inversion center. So molecules which have inversion centers, here carbon dioxide, the midpoint.
Madam,
One,
can you show the earlier one, previous slide?
this one.
Okay, here the inversion means H1 all same, no? The numbers.
Hydrogens are labeled for your convenience, but all these are
Yeah.
hydrogen atoms. No, so when you take the midpoint and extend the line here, and then you extend the line, you get the same atom. So it's an inversion center. Okay. Not only that, even the carbons to this bond, you get equal distance, the two carbons on either side. Right?
Okay.
Okay. So these are molecules with inversion centers. Carbon dioxide, here trans 1,2-dichloroethene. So here, again, when you draw, you get 2 chlorine atoms on either side. Similarly, here 2 hydrogen atoms. Then this is trans 1,2-difluorodiazine. Okay. Here PTCl4. Right? So when you draw a line, you get the equal distance. You get from the center, platinum molecule atom is the center. So you get equal atoms on this side. Similarly, staggered
That
form of
means, Madam, excuse me, that means we get Cl1 at Cl3 place, right?
Yeah, along this. Now this is the midpoint now. So when you draw a line towards Cl on the left side, and when you draw a line to this bond on the right side, you get equal atoms, chlorine, chlorine. And again, this side, this way also the same. So platinum has the midpoint, it is the inversion center. Yes. Right. In staggered form of ethane, again you get a midpoint because from here to here, right? You can draw a line. 2 equal atoms are there. Here to here and here to here, right? So make a model and see, then you can understand. Similarly, in benzene, you get inversion center in the middle of the molecule. Then hexafluorosulfur, oh, yeah,
Excuse me,
sulfur
madam.
yeah,
Suppose now there's a trans 1,2 dichloroethene, right?
yeah,
So if there's cis 1,2
yeah.
dichloroethane,
Cis means you get this chlorine atom here. We
and
consider
both
like
the
that,
H,
and then it won't have.
it won't have, right?
No, it won't have, because this side you have
Okay,
chlorine
fine.
and this side you have hydrogen, right? So no center of inversion center against SF6, right? So each side you have similar atoms. So you get midpoint, the inversion center. So all these molecules are having inversion center, right? Now I skipped one slide. Molecules with no inversion centers. This type of molecules does not have inversion centers. Trigonal planar molecule. BF3 is the example, right? No inversion center. Tetrahedral molecule. Pyramidal molecules. Trigonal pyramidal. Square pyramid. Pentagonal planar and pentagonal pyramidal. So that sort of molecules does not have any inversion center. Right. Then we'll come to improper axis. Right? So, and improper rotations. Operation of a rotation about an axis followed by reflection through a plane perpendicular to this axis is called an improper rotation. So, you do an rotation operation followed by reflection through a plane perpendicular to this axis. It's called improper rotation. So an object is said to have improper axis of symmetry if rotations about the axis through 360 over n, followed by reflection through the plane perpendicular to that axis leaves an orientation indistinguishable from the original one. So you have to do a rotation operation and a reflection operation. But the reflection has to be perpendicular to the rotation axis. That is the criteria, right? So, and that is called the improper axis. So, whether you do the rotation first, reflection later, or you do reflection first and rotation, it's the same. Okay? So, we'll take methane molecule, right? Now, we labeled 1, 2, 3, molecule A. You rotate it by 90 degrees, right? C4 axis, so therefore you get this molecule, the molecule B. Is that clear? When you rotate it by 90 degrees, these two H's will lie on the plane of the paper and the other two, one goes in and one other comes out, right? Then you do the reflection perpendicular to this rotation, right? So C4 you rotate and you have a reflection, horizontal plane in between. Then you get this molecule. The reflection will give you hydrogen here, fourth number, hydrogen labeled 4 here, and these two on the plane of the paper, which is the original configuration. So here we have taken two indistinguishable orientations. After doing a C4 operation and a reflection perpendicular to that. So this methane molecule therefore has S4 axis rotation, improper rotation. Okay? Is that clear? Yes
Can
or
you
no?
explain B configuration?
Sorry?
Can you explain B figure?
B figure. Now, dear, this A figure, these two lie on the plane of the paper. And this is going inside and this is coming out. That is tetrahedral arrangement, right? Now, when you rotate it 290 degrees, right? 90 degrees you rotate. Then what happens? These two come on the plane of the paper, 1 and 2. Hydrogens marked 1 and 2. And these two will, one will go coming up and then other one will go inside. You rotate it by 90 degrees anticlockwise now, right? So you get this operation. And after that, you do a reflection perpendicular to that rotation axis, right? So you keep a mirror and then get the reflection. So this is the reflection. The one hydrogen that is, these two are on the plane of the paper, so no issue, it will appear like that. But here the hydrogen label 3 is coming out of towards you. So it will stay when you reflect on top towards you, right? And here the hydrogen labeled as 4 go inside and then that will keep this in place, right? So you get the A and C same indistinguishable orientation. So it is called the S4 rotation axis. Now is it clear? First you do the rotation and then the reflection perpendicular to that axis. Still you are confused.
Madam, can you explain the C4 rotation A to B?
A to B.
Yes.
So here I said these two hydrogens labeled 3 and 4 lie in the plane of the paper, right?
Okay.
Here one is going inside and other one is coming out. That's how you draw these bonds now. Okay? So you rotate it by 90 degrees.
90 rotation.
Consider this part, when you rotate it by 90 degrees, one will come out, other one will go in, right? So this is rotated by anti-clockwise. So the hydrogen label 3 will come up, right? Other one will go inside the plane of the paper. And these two will lie on the plane of the paper. That's all.
Is
C4
okay,
operation.
madam. 1, 2, 4, 3 is on the paper. That is top one has to be 3. The B figure, the numbering, hydrogen numbering.
Yes, correct.
Correct.
When you rotate this, now consider these two, this lie on the plane of the paper, no? So when you turn it anti-clockwise, you keep your hand and then rotate and see what happens. 90
One
degrees
comes, yeah, one comes out, one goes
in.
in.
These
Alright.
two will lie on the plane of the paper.
All right, right. Okay,
Okay.
madam.
You have your own models and then study these things. Then it's easy for you, right? So it's a S4 operation. Again, Aline, you can rotate it C4 and then reflect through the center carbon atom. You get the equivalent orientation. So indistinguishable. So you say it's an S4. Then the staggered ethane. Right? You have the staggered molecule. You rotate it through this 60 degrees C6. And then you have this configuration. Right? These are not labeled hydrogen. So you have to think for yourself and label. And then now this is along this C6 the rotation axis and you get a reflection perpendicular to that. So then you get the same molecule. Indistinguishable orientation. A and C are indistinguishable. So this is the S6 operation based on this angle of rotation. Okay? First you do the rotation and then you reflect it perpendicular to the rotation axis. Right? Then we have the eclipse form of ethane. Again here, these two going inside, these two are coming out, and these two are lying on the plane of the paper. So you do a C3 operation, right? When you do a C3 operation, what happens? One hydrogen labeled 1 will come here. This 3 will go here and 2 will go here, right? So similarly, 1 prime goes down, 2 prime goes up, goes inside, and then 3 prime comes here. Then you do a reflection center of the molecule perpendicular to the C3 axis and you get the indistinguishable orientation. Okay, so it has S3 improper rotation. Then boron trifluoride, right? So here 1, 2, 3, you rotate it 120, C3, you get, right? 1 going here, 2 coming here, and 3 going here. This is a C3 operation, right? So it is this axis. Now what we have to do? We have to do a reflection perpendicular to this C3 axis, right? So perpendicular means it's the plane of the molecule. So plane of the molecule is this. So when you do a sigma H, that means when you bisect all 4 atoms horizontally, you get the similar structure. And that is, again, both you get a indistinguishable orientation. So it has S3 improper rotation. Okay? Yes or no? Any doubts?
Madam,
Why
can I
no?
explain A to B?
Sorry, A to B.
Yeah, madam.
Now along this bond boron atom, right? Perpendicular, this is a planar molecule now. Perpendicular to the plane only, we rotate it 120. Now here, this is a planar molecule, bond angle is 120. So you rotate it by 120, that means C3 rotation. And then these positions change. When you rotate 121, the F labeled 1 will go here, F labeled 2 will come here, and 3 will go here. Okay? So after that, you do the reflection through these boron atoms, through these 4 atoms, boron and 3 fluorine atoms, the plane of the molecule. So it's a sigma H operation because this is, it lies along the boron atom and plane of the molecule is perpendicular to that. So that is again another S3 operation. You get the indistinguishable configuration. That's all. Is it clear now?
Clear, madam.
Okay. Right. This is a summary. Right. Then, so we'll come to the last session. I just took one part of it only because other part I could not find the figure. Right. So go home and read that one. How do you predict whether a molecule can have a dipole moment? Right. So in your book, the last session gives the applications and that gives you how to predict the I turn to this book. Yeah. Simple applications of symmetry of molecules in chemistry. Right? So you predict whether a molecule can have a dipole moment or not based on these two rules. So rule 1, if a molecule has a rotation axis, so then the dipole moment of that molecule, if there is a dipole moment, it must lie along this axis, along the rotation axis. Okay? Give me 1 second.
Madam, we can't hear you.
Sorry, I muted. No, I got a call. So you went through this now? Rule 2, a molecule with at least two non-coincident rotation axes cannot have a dipole moment, right? So here, PTCl4, we have C4 rotation, which goes through the platinum, and it does not have a dipole moment because here all four electronegative atoms, these things cancels out. So there is no rotation axis, sorry, there's no dipole moment in this molecule. Then again, methane. We have, if you consider this, and we have this C3 rotation, right? Each hydrogen atom we can consider and we can have C3 rotation, but it does not have the dipole moment along this C3 axis. So therefore, it is not a, it does not have dipole moment. Similarly, BF3. But when you take these two molecules, chloroform, CHCl3. Now, along this CH bond, right, we have a rotation axis. What is it? C3, right? And your dipole moment also lies along that axis. So therefore, CHCl3 has a dipole moment. And here also in water molecule, right, we have a C2 axis. And then the dipole moment also lies along this C2 axis, right? You have studied in level 3, unit 2, right, the dipole moment of molecules after studying the bonding. So here you get dipole moment, right? So that's all I could do for today. So I thought I will give you more and more examples and show you those structures so that you get a clear idea. Now go through the book again and then try to do the activities. All the activities, the answers are there, so you can get a better idea of this symmetry. And it's very simple, right? Try to answer the questions. The MCQs are also there and the review questions. Don't have the answers, but once you know the subject, you can answer those things. And if we get another day, maybe for the revision day school, I will bring some questions and do. Okay?
excuse me, madam.
Mm.
Could you please
Yes.
upload this recording to LMS?
Yes, surely. We have to.
Because they have already uploaded day school 5 of last year. But I hope this presentation and explanation would be helpful, more helpful for
Yeah,
us.
this recording will be uploaded. Don't worry.
Okay, thank you,
Yeah,
madam.
of course, we cannot, but by tomorrow, I will send it to Dr. Kokila. She will do the uploading. Okay?
Okay, thank you. Okay, thank you, madam.
I hope you got an idea about symmetry of molecules. Yes or no?
Yes, madam.
Okay, good. So now you will be able to answer the CAT questions.
Madam, there's a small doubt in the book. There are questions, review questions.
Huh?
Symmetry of a molecule is determined by its electron density distribution. Is it correct, madam?
Is it electron density distribution or
Yeah.
the nuclei?
Nuclear skeleton, density distribution. Both are
Yeah,
there.
but at the first session, I saw everything is given in the first session, right? I saw that question.
Yeah.
So
Only the nuclear skeleton, right, madam?
only the nuclear skeleton,
Okay.
not the electron distribution, right? We don't consider the electron distribution. So did you get any idea? You got a better clarification of the doubts you had? At least some knowledge? Yes or no?
Yes.
Yes, madam.
Good. So now go through the book, right? Read the book carefully and try to understand, and also check the recording. You will get a better idea of how to answer the questions. Just simple theory is enough, right? When you are given a molecule structure, you have to visualize it and then see the rotation axis, the symmetric planes, the inversion centers. Sometimes some molecules have everything, right? Now, if you take benzene, it has an inversion center also. So all that depends on those five symmetry elements: identity, axis of rotation, symmetry planes, improper rotation, and then inversion center. Those are the things you have to study. So one by one, study as much as possible the examples given in the book also, and then try to, if you can, make some models with clay and whatever, using pencils. I used to do it like using 3 colors of pens and pencil. You make the model and then see for me. Then it's easy for you to understand, right?
Madam,
So that's
in benzene, madam, in the book, they have mentioned only we can get C6 and the C2. C3 also there, right, madam?
E3 also there.
Okay.
So if there is C6, definitely C3 has to be there. No? C6 means 60 degrees. So twice that is C 120 angle, no? So it has to be there.
Yeah.
Okay.
Madam, can't we get answers for the review questions?
Sorry.
Can we get answers for the review question?
Review questions, you have to go through and find the answers. If you have any doubts, you can ask me, right? Send me a mail. But the answers are not given. So after going through the book, I just went through this whole book, right? And then I went through the review questions. So if you understand the book, you can answer those. It's easy.
Okay.
It's not hard. Don't think that it is hard, but you have to go through the material first, course material, and then answer the questions. Right? If you have any doubts, you send me a mail. Okay?
Okay.
Are you satisfied with today's day school?
Yes, madam.
Yes.
Yes, ma'am.
Yes, madam. Thank you.
Okay, good. I want to hear all your voices, only very few who are speaking. Anyway, all the best. Do well at the exam, right? Good luck.
Thank you, madam.
Thank you,
madam.
Thank you,
Ah,
madam.
okay. So I will end the meeting.